Welcome back to another video at the channel, and today we will be looking at a number theory problem. So define the sequence a1 equals to 2 and an equals to 2 to the power an minus 1 plus 2 for n larger equals to 2. Prove that an minus 1 divides an for all positive integers n larger or equals to 2. So this problem is taken from ELMO. Even though the name might not sound very intelligent, it is a competition that is actually set by the members of the USA Math Olympiad team. So it is actually not that simple. So we'll be looking at one of the problems is P1 of 6, and let's move on. So a method we will be using today will be strong induction. So you might have heard of mathematical induction, but strong induction is basically a stronger version of it. And please don't click away because you don't understand what the hell is going on. We have an example on the next slide which should hopefully explain it better. So let Pn be the statement you want to prove where n is a positive integer. Note that when you use induction, n must be a positive integer. It doesn't work on negative numbers, doesn't work on rational numbers, irrational numbers, etc. So to use it, we have to first show that the base cases are true. So verifying pk0 is true. So k0 can be anything. It can be 0, 1, 2, but it must be the first number in the sequence, let's say, you want to prove. So, and we assume pk0 plus 1 all the way to pk minus 1 is true. Then we show that pk is true. So I'll be showing an example in the next slide. The example I was talking about is prime factorization. So essentially, it is pretty trivial that any number, natural number, can be expressed as the product of primes. So let's say 4, 2 times 2, 36 will be 2 squared times 3 squared, etc. And so how do we prove it? We'll be using strong induction. Let Pn be the statement that any natural number smaller than n, larger than 1 can be expressed as the product of prime and 1. So let's say we have the base cases P2, and 2 is equals to 2 times 1. Therefore, the base case holds. If you want to do one more, let's say 3 as your base case. So let's say P3 will be equal to 3 times 3, 3 times 1, and the base case holds, and P4 2 times 2, P5 1 times 5, etc. That will be our base cases. So we assume that all these numbers, all these statements, P2, P3, all the way to pk minus 1, holds for some integer k. That is, any natural number smaller than k, larger than 1, can be expressed as the product of primes and 1. So let's continue. That means we can let k equals to n times m for some nm natural numbers nm, and they are not equal to 1. And clearly nm are smaller than k. So case 1, if one of them is prime, then the statement holds very clearly. And case 2, if both of them are not primes, then by our hypothesis, n and m can be written as product of primes and 1, which implies k can be rewritten as products of primes and 1. Therefore, the statement holds. So let's say we have 16, and 16 will be equals to 4 times 4. And since our base case says that 4 can be expressed as the product of primes times primes. So let's say 4 equals to times 2 and 4 equals to times 2. So 16 can be expressed as the product of primes and 1. Therefore, our hypothesis holds for all natural numbers. That means we can let Pn be the statement that an minus 1 divides an for all positive integer n larger equals to 2 in the sequence 2 to the power an minus 1 plus 2 for n larger equals to 2, a1 equals to 2. And our base case P2 is 6, and a1 divides a2 clearly because 2 divides 6. And to continue the base case, we have P3 is equal to 66, so we have a2 which equals to 6 divides 66. Therefore, our base case holds. So we can assume P2, P3 all the way to pk is true for some k, natural number k, and we strive to prove that pk plus 1 is true. That is, ak minus 1 divides ak. So first of all, we have to mention some useful formulas. So x to the power m minus y to the power n will be equals to x minus y times x to the power m minus 1 times y plus all the way up to y to the power n. And this is true for all integers, positive integers n. And the second formula we're going to use is x to the power n plus y to the power n will be equals to x plus y times x to the power n minus 1 times y minus all the way up to y to the power n. And this is true for only odd integers n, odd natural numbers n. It does not hold for any even numbers. So if you want to verify these, you can simply expand the brackets and you can see it's actually pretty trivial. So let's move on. We will be using some useful lemmas. These are lemmas that are actually pretty classic and seen a lot. So I suggest you remember them and sing as a formulas. So firstly, the first lemma is 2 to the power a plus 1 divides 2 to the power ab plus 1 for all odd b. So the proof is you can use the previous formula 2. We have 2 to the power ab plus 1 equals to 2 to the power a to the power b plus 1 to the power b. And it will be equals to 2 to the power a plus 1 times 2 to the power a to the power b minus 1 minus and over plus 1. And therefore, you can clearly see 2 to the power a plus 1 is a factor of 2 to the power ab plus 1. And lemma 2 will be kind of similar. So 2 to the power a minus 1 divides 2 to the power ab minus 1 for all natural number b's. This time it's not only odd numbers but also even numbers. And we will have 2 to the power ab minus 1 will be equals to 2 to the power a to the power b minus 1 to the power b. And will be equals to 2 to the power a minus 1 times the rest. So we can clearly say 2 to the power a minus 1 divides 2 to the power ab minus 1. And this is the application of formula 1, which I've mentioned above. This implies using strong induction, we would have ak minus 1 divides ak, which is our inductive hypothesis. It is equivalent to 2 to the power ak minus 2 plus 2 dividing a2 to the power ak minus 1 plus 2. And here we note that an is equals to 2 to the power an minus 1 plus 2. And therefore, using our hypothesis, we can first cancel out the 2's. We will have 2 to the power ak minus 2 minus 1 plus 1 dividing 2 to the power ak minus 1 minus 1 minus 1 plus 1. And using our lemma, we will have ak minus 2 minus 1 dividing ak minus 1 minus 1. And since an minus 1 is odd for all n, we can notice that we can actually use lemma 1 successfully. So this is equivalent to applying the formula. Again, we will have 2 to the power ak minus 3 plus 1 dividing 2 to the power ak minus 2 plus 1. And here, notice that an is equals to 2 to the power an minus 1 plus 2. And this will be equivalent to our inductive hypothesis, which is ak minus 3 dividing ak minus 2, because they are both odd numbers, so we can apply lemma 1 again. So it concludes our proof because inductive hypothesis can lead to ak minus 1 divides ak. And our proof is complete. And I hope you're not too confused in this video. If you are still confused, I suggest you to maybe go online and search strong inductions for some examples and understand them more clearly, because induction, strong induction, and there are many more types of inductions, are very useful in handling Olympiad problems, or even like, let's say, high school or university mathematics. It's pretty vital and fundamental. So guys, I hope to see you next time in our next video, and we'll be doing number theory again. And I hope to do some more geometry, but it's might be time consuming, but I will try my best. So thank you, everybody.